On April 4th, 2026, a comet from one of the most dangerous families in the solar system is heading directly into the Sun during solar maximum. It was spotted earlier than any comet in its family has ever been spotted. It is brightening at a rate that implies something substantial at its core, and the last time something like this grazed the solar corona, a solar storm so powerful that telegraph wires caught fire swept across the entire planet. Most scientists will tell you not to worry, but a small number of them are very quietly not sleeping well. Stay with me until the end of this video, because what comes next is the part nobody is talking about. If this has you hooked, subscribe to the Skylab, because as Comet C 2026A1 dives toward the Sun, we'll be here tracking every development. Drop a comment telling me where you are watching from, and tell me honestly, do you think this one vaporizes quietly? Or do you think the Sun is about to remind us who is actually in charge of this solar system? Now let's get into it. Part 1. The day the data started looking strange. Something was out there, and it was getting brighter much faster than it should have been. In early 2026, a routine sweep of the sky by one of the modern automated survey programs caught a faint smudge of light moving against the background of distant stars. At first, it barely registered as unusual. The sky's full of faint moving objects. Most of them are boring. Most of them are small, cold, and completely indifferent to our existence. But this one was different, and the astronomers who noticed it began to feel that particular brand of unease that comes from data that refuses to behave the way it is supposed to. The object was catalogued as Comet C 2026A1, and it belonged to a group of comets with a reputation. They are called the Kreutz sungrazers, and that name alone should tell you something. These are comets that do not politely orbit the Sun from a comfortable distance. They plunge directly at it. They dive into the corona, the outer atmosphere of our star, at speeds that would make your head spin, and most of them do not come back out. They are, in the most literal sense, kamikaze comets. The reason this particular discovery raised eyebrows immediately was the detection distance. Astronomers found C 2026A one much farther from the Sun than any previous Kreutz comet had ever been spotted. And that matters enormously, because the faintness of a comet depends on how much light it reflects. If you can see something from very far away, it means one of two things. Either it is unusually large, or it is unusually active, releasing enormous quantities of gas and dust that catch sunlight and glow. Neither explanation is boring. At the moment of initial detection, the comet sat at around magnitude 18. That is extremely faint. You would need a serious telescope just to find it. But then something remarkable happened. By early March of 2026, it had brightened to around magnitude 11. Now, if you're not familiar with the magnitude scale, let me give you a quick translation. Each single step on the magnitude scale represents an object about 2.5 times brighter. The comet moved 7 full steps. That means it became not 7 times brighter, not 70 times brighter, hundreds of times brighter, in a matter of weeks. That is not normal behavior for a rock and ice ball traveling through space. What made observers even more attentive was the shape of the brightening curve. When a comet nucleus fragments, when it literally cracks apart from the stress of solar heating and gravitational tidal forces, the brightness tends to spike erratically. You get sudden jumps followed by plateaus or declines. What they saw instead was smooth, consistent, a steady, almost elegant climb in brightness that suggested the nucleus was holding together intact, building towards something. A smooth, brightening curve on a Kreutz sungrazer means you are probably looking at something physically substantial heading straight for the Sun. A geophysicist named Stephen Burns took notice publicly and suggested that this comet could become one of the most significant sungrazer events in decades. When a scientist who studies Earth's physical system starts paying close attention to a comet, that is worth pausing on. The perihelion date, the moment of closest approach to the Sun, was locked in for April 4th, 2026, and the distance at perihelion was approximately 0.005 astronomical units. An astronomical unit is the average distance from Earth to the Sun, roughly 150 million kilometers. 0.005 of that is around 750,000 kilometers. That sounds like a lot until you realize the Sun's surface is already about 696,000 kilometers from its own center, meaning this comet would be skimming just 50,000 kilometers above the solar surface. That is inside the corona. That is inside the Sun's outer atmosphere. That is not a flyby. That is a plunge. Here is the detail that should make the back of your neck prickle slightly. The last time a comet of significant size interacted with the solar corona, observers noted that a coronal mass ejection erupted in the aftermath. Now, scientists are careful about the word caused. They will tell you that correlation is not causation, and they are right. But there it was. A large sungrazer goes in, and shortly afterward the sun throws a billion-ton cloud of plasma into space. Whether that was coincidence or something more is exactly the question that astronomers are now preparing to answer. Because C/2026A1 is on its way in, it is getting brighter by the day, and April 4th is coming fast. What happens in the final 10 days before this comet reaches the sun is where the story gets genuinely strange. Part 2. The 10-day plunge into the sun's gravity well. Speed is one of those concepts that sounds simple until you really sit with it. In early March of 2026, Comet C/2026A1 was sitting at roughly 1 astronomical unit from the sun, the same distance as Earth. From the outside, that sounds manageable. 1 astronomical unit, a familiar number. But the comet was already moving at tens of kilometers per second at that point, and the sun's gravity had not yet really gotten its hands on it. By late March, the comet would cross the half AU mark. It covered the equivalent of half the Earth-Sun distance in just a few weeks, which should give you a sense of the acceleration beginning to build. Physics has a concept called gravitational potential energy, and the way it works is straightforward. The closer you fall toward a massive object, the more that stored energy converts into speed. A ball dropped from a table moves faster than one dropped from a centimetre off the ground. Now imagine the table is replaced by the sun, and the ball is a comet made of ice and rock several kilometres across, and the drop is measured in millions of kilometres. The numbers become extraordinary. Sungrazers approaching perihelion routinely exceed 500 kilometres per second. For context, a bullet travels roughly 1 kilometre per second. We are talking about 500 times the speed of a bullet sustained for millions of kilometres of travel. This is not a gentle approach. This is a freefall into the most powerful gravitational environment in our solar system. The comet's ephemeris, which is the technical term for the mathematical prediction of where an object will be at a given time, was being refined continuously throughout March. This is not unusual. Every new observation slightly adjusts the calculations. A little more data here, a slightly tighter arc measurement there, and the prediction sharpens. But here is the unsettling part. When an object is still relatively far away, even small measurement uncertainties can translate into large differences in the predicted final position. The margins shrink as the comet closes in, but in the early weeks the error bars were wide enough that some astronomers noted something uncomfortable. A direct solar impact could not be completely ruled out. Let that settle for a moment. Not a near miss, an actual impact with the sun itself. Now, before you spiral into catastrophizing, the sun is an enormous object. A comet hitting the sun is not an extinction event for Earth. The sun has been hit by countless objects across its 4.5 billion year history and has not noticed. What matters is not the physical impact itself, but what that impact injects into the solar atmosphere. A comet nucleus estimated to be several kilometers in diameter, travelling at hundreds of kilometers per second and striking the solar corona directly, would release an extraordinary quantity of material into an already active, energetic, magnetically complex environment. That material does not just disappear, it interacts. Even on a non-impact trajectory, the comet's behaviour during those final 10 days was going to be watched with unusual intensity. Each day of the final approach brought the comet into regions of increasingly ferocious solar radiation. At 1 astronomical unit, the sun's energy is what we feel standing outside on a clear day. At 0.1 astronomical unit, radiation intensity is 100 times stronger. At 0.01 astronomical unit, you're talking 10,000 times stronger. By the time the comet reaches perihelion at 0.005 astronomical units, the radiation environment is so extreme that most materials known to science would simply cease to exist as solids. And yet, the nucleus was holding together. The smooth, brightening curve continued. Whatever was at the centre of this object was surviving conditions that should have begun destroying it well before perihelion. Picture it like this. You're watching a piece of ice thrown into a furnace from a distance. You expect it to vaporise immediately on contact with the heat, but instead it keeps travelling. It moves through the flames, it survives longer than it has any right to, and the entire time it is releasing enormous clouds of steam and gas into the fire around it. That is the comet. That is what is happening in those final 10 days. The question that the solar physicists were beginning to ask quietly among themselves was not just whether the comet would survive. It was about what its gas and ice and dust would become once they entered a truly alien environment. Because the sun's corona is not just hot, it is plasma. It is a seething, magnetized, electrically charged state of matter that follows completely different rules than the solid, liquid, and gas we are used to. And what happens when comet material enters that environment is something that most people have never thought about, and probably should. Part 3. The plasma problem. No one talks about. The sun's outer atmosphere defies one of the most basic expectations in all of physics. If you heat something, the farther you get from the heat source, the cooler it gets. That is how campfires work. That is how ovens work. That is how virtually every source of heat in everyday life behaves. The sun breaks this rule completely. The visible surface, the photosphere, sits at around 5,500 degrees Celsius. Reasonable for a star. But the corona, the wispy outer atmosphere extending millions of kilometers into space, somehow reaches temperatures between 1 million and 3 million Kelvin. The atmosphere is hundreds of times hotter than the surface below it. This paradox has puzzled physicists for decades and is still not fully resolved. At a distance of 0.005 astronomical units from the Sun, a comet does not simply encounter heat. It encounters a completely different category of physical reality. Solar radiation at that proximity is roughly 40,000 times more intense than what reaches Earth. The ices that make up a comet's nucleus, water, carbon dioxide, ammonia, carbon monoxide, begin vaporizing violently. But vaporizing is not the final stage of this process. It is just the beginning. The gas released from the comet nucleus, moving outward at speeds of perhaps a kilometer per second, immediately encounters the corona's extreme temperature and radiation field. At those energies, neutral atoms cannot hold on to their electrons. The atoms become ionized. They lose electrons and become electrically charged particles, which is just a technical way of saying they are no longer ordinary gas. They have become plasma. This is where the physics shifts dramatically. Neutral matter responds to gravity. Plasma responds to something else entirely. It responds to magnetic fields, and the sun's magnetic field in the corona is complex, twisted, and carrying enormous amounts of stored energy in ways that are not immediately obvious from the outside. Think of it this way. Imagine you release a cloud of iron filings in a room with no magnetic fields. They just drift randomly. Now introduce powerful magnets throughout the room, and suddenly every particle snaps onto a field line and moves in a completely different pattern than you expected. The comet's vaporized, ionized material does not drift randomly through the corona. It gets captured by magnetic field lines and begins flowing along them, creating what physicists call a plasmoid, a coherent, structured blob of plasma moving through a magnetized environment. The plasmoid is not just floating there, it is moving at hundreds of kilometers per second, threading through a region of the corona that contains long, arching structures of twisted magnetic energy called filaments. These filaments are in a constant state of tension. They are, in a sense, like stretched rubber bands. They store energy, sometimes for days or weeks, in a kind of magnetic potential that is just waiting for a trigger. Now here is where the scientific community gets careful and cautious, and rightly so. The explicit claim that a comet can cause a solar eruption is not supported by consensus. Solar physicists will tell you clearly that the sun releases incomparably more energy than any comet could supply. The sun does not need a comet to throw a coronal mass ejection into space. It does this constantly, especially during solar maximum, which is exactly where we are right now. But some researchers have proposed something more subtle. Not that the comet creates an eruption, but that it might trigger one. The difference is significant. A trigger does not supply the energy. A trigger releases energy that was already there, already stored, already primed. Like the last snowflake that starts an avalanche, the avalanche was not caused by one snowflake. But that snowflake tipped a system that was already at the edge of instability. Whether a comet plasma cloud moving along solar magnetic field lines could disturb a filament that was already close to erupting is the open question. And it is one that the arrival of C/2026A1 could help answer. The historical record suggests this is not a completely new idea. It is an idea with precedents that are, depending on your comfort with uncertainty, either reassuring or deeply inconvenient. Part 4. The sungrazer CME correlation. Correlation is the most dangerous word in science and also the most seductive. The Solar and Heliospheric Observatory, known as SOHO, has been watching the Sun continuously since 1995. It carries a device called a coronagraph, which essentially blocks out the bright disk of the Sun so that the faint structures around it become visible. In that time, SOHO has catalogued well over 4,000 sungrazers. Most of them are tiny. We are talking fragments only a few meters across, probably debris from larger comets that broke apart long ago. They drift in, they vaporize in the corona, and nobody writes a news article about it. They are the background noise of our solar neighbourhood, but occasionally something larger comes through, and when it does, solar astronomers watch very carefully. Because scattered through the observational record, there are cases where sungrazers of meaningful size pass through the corona, and in the time frame around that passage, coronal mass ejections erupted. Not every time, not even most times, but enough times that a small number of researchers began asking whether the relationship was more than coincidental. The problem with answering that question is maddeningly simple. The Sun during solar maximum is producing CMEs constantly. On any given day near peak activity, the Sun might launch several CMEs into space. So if you observe a sungrazer, and then, hours later, see a CME, what exactly have you proven? You could argue you have proven nothing at all. You could also argue that the timing and directionality of specific events suggests something more than random chance. Both arguments have been made in peer-reviewed literature, and neither has definitively won. Solar physicists who are skeptical of the triggering hypothesis have a very reasonable position. The energy in a large CME can be on the order of 10 to the 25 joules. That is roughly the energy of 10 billion atomic bombs. The energy a comet could inject into the corona, even a large one, is many orders of magnitude smaller. It seems physically absurd to suggest that a small plasma cloud could somehow cause a system to release energy at that scale. The skeptics are not wrong to be skeptical, but the advocates of the triggering hypothesis are not arguing about energy. They are arguing about information, about timing, about whether a small perturbation in a critically balanced system can initiate a cascade. And the history of physics is full of systems where the initiating event and the resulting energy release are wildly disproportionate. That is what makes complex magnetic systems so interesting and so unpredictable. The scientific literature has not reached consensus. That sentence deserves emphasis. This is not a settled debate with a clear answer. It is an active, open, genuinely contested question. And the reason it has remained unresolved for decades is largely observational. Most sungrazers are simply too small to produce any detectable effect on the corona, regardless of what the theory might predict. They vaporize like dust on a griddle. No experiment, no data, no resolution. C/2026A1, if current brightness estimates are accurate and the nucleus is truly substantial in size, could change that. It could be the first large-scale natural experiment in comet-corona interaction that modern solar observatories are actually equipped to capture in detail. Parker Solar Probe, Solar Orbiter, SOHO, ground-based solar telescopes of unprecedented resolution, all of them positioned and active during a moment that the solar physics community will not want to miss. The data from this event could either close the debate or deepen it. And there is one scenario, sitting at the far end of the probability distribution, that researchers discuss in careful language but discuss nonetheless. It is the scenario that keeps the space weather community awake at night, not because it is likely, but because of what it would mean if it happened. Part 5. The Black Swan Scenario. Rare things happen. That is almost a tautology, but it contains something important that humans are genuinely bad at processing. The term black swan comes from a philosophical thought experiment. For centuries, Europeans assumed all swans were white, because every swan they had ever seen was white. The assumption was not irrational. It was based on enormous amounts of evidence. Then explorers reached Australia and found black swans. Suddenly, an assumption that had seemed unquestionable was wrong. The lesson was not that evidence is useless. The lesson was that absence of evidence for a rare event is not the same as evidence that the event cannot happen. The black swan scenario for C/2026A1 has a specific chain of events that researchers sometimes walk through, always carefully, always with appropriate hedging, but walk through nonetheless. Here is how it goes. The comet survives the initial thermal assault and penetrates deep into the solar corona, as Comet Lovejoy did in 2011. The nucleus fragments under tidal stress, but instead of a gradual vaporization, it releases an enormous concentrated pulse of ionized material over a short period. That plasma cloud, moving at hundreds of kilometers per second, threads along a specific set of magnetic field lines that connect to a filament region that is already in a state of marginal stability. The plasma perturbation is enough to initiate magnetic reconnection in that region. Magnetic reconnection is the process by which oppositely directed magnetic field lines snap together, cancel out, and release their stored energy almost instantaneously. And a coronal mass ejection erupts, a truly massive one, during a period of solar maximum when the sun's magnetic activity is already elevated. Each individual step in that chain has physical justification. The question is whether all those steps happen in sequence, at the right place, at the right time. The probability of any one step is uncertain. The probability of the full chain is much smaller, but much smaller than uncertain is still not zero. If such a CME were directed toward Earth, the consequences would depend heavily on the magnetic orientation of the eruption. A CME that arrives with its magnetic field pointing south, opposite to Earth's magnetic field, couples efficiently with our magnetosphere and drives the most powerful geomagnetic storms. One that arrives pointing north mostly slides past. The direction is not predictable until the eruption is already heading toward us. The historical benchmark for extreme geomagnetic events is the Carrington event of 1859. A solar storm of extraordinary magnitude struck Earth's magnetic field and induced currents in telegraph networks across the world. Telegraph offices reported sparks leaping from equipment. Operators received electric shocks. The auroral display was visible near the equator in regions that had never seen northern lights in recorded history. People in the northeastern United States reportedly woke in the middle of the night because the aurora was bright enough to read by. Telegraph infrastructure in 1859 was primitive compared to what we have today. Our civilization now runs on power grids, satellite networks, GPS systems, and internet infrastructure that are all sensitive to the electromagnetic effects of severe geomagnetic storms. The Carrington event happened before any of that existed. If something comparable hit today, the conversation would be very different. Could a large sungrazer interacting with an already active sun during solar maximum meaningfully increase the odds of such an event? The answer is possibly, and that possibly is doing a lot of work. Most likely April 4th passes quietly. The comet puts on a spectacular show for solar astronomers, and that is the whole story. But the universe does not guarantee most likely outcomes, it just makes them probable. How we got to this moment of uncertainty stretches back much farther than 2026. It stretches back to a dynasty of solar destruction that has been operating for centuries. Part 6. The Kreutz dynasty. Somewhere in the distant past, perhaps centuries ago, perhaps longer, a comet of extraordinary size made a fatal approach to the Sun and did not survive intact. Astronomers believe the Kreutz sungrazer family is the scattered wreckage of that ancient encounter. A massive progenitor comet, possibly tens of kilometers across or larger, came too close to the Sun and was torn apart by tidal forces. Gravity is not uniform. The side of an object closer to a massive body like the Sun is pulled harder than the far side. For small, loosely bound objects, that differential pull can overcome the internal cohesion holding the object together. The comet fractured, and its pieces, while following slightly different paths, all shared one common destiny. They would continue returning to the Sun on nearly identical orbital tracks, plunging close to the solar surface again and again over the centuries. The orbital geometry of the Kreutz family is their defining characteristic. They all share paths that bring them within a few solar radii of the Sun's surface at closest approach. Some of them make it through, many do not. The ones that do come back around again thousands of years later, slightly smaller each time, leaving a trail of debris that stretches across millions of kilometers of space. The family has produced some of the most spectacular comets in recorded human history. The Great Comet of 1843 developed a tail that extended over 300 million kilometers into space, one of the longest cometary tails ever observed. It was visible in daylight, near the Sun, in broad sunlight, which is an astonishing thing to contemplate if you have ever tried to see a faint comet in a dark sky with your eyes adapted to the darkness. The Great September Comet of 1882 was so brilliant that observers reportedly could see it even while looking almost directly toward the Sun. Comet C in 1965 remains one of the brightest comets of the 20th century, producing a tail visible before sunrise to observers across the planet. All of these extraordinary objects came from the same ancient source. They are pieces of something that no longer exists as a whole, and since SOHO began watching in 1995, astronomers have catalogued thousands more Kreutz fragments, nearly all of them insignificant in size, a few meters, maybe tens of meters for the larger ones. They evaporate without ceremony. C/2026 A1 is behaving like it does not belong in that category. Its brightness implies something physically significant at its core, a nucleus that has survived long enough to announce itself from an unusual distance, that is continuing to brighten smoothly, that is heading toward the Sun with all the energy and momentum of a large surviving fragment from that ancient fragmentation event. The question of size is difficult to answer, precisely because the brightness of a comet comes from the coma, the cloud of gas and dust surrounding the nucleus, not the nucleus itself. You cannot look at a bright comet and simply read off its diameter, but the behavior of this comet is consistent with previous large Kreutz sungrazers, and there is one previous large Kreutz sungrazer that serves as the closest comparison we have, one that surprised everyone who thought they knew what a sungrazer could do. Part 7. The Lovejoy Precedent. Astronomers have a complicated relationship with being wrong. They are professionally trained to resist it, and yet the history of astronomy is essentially a long series of corrections. In late 2011, an amateur astronomer in Australia named Terry Lovejoy discovered a comet that turned out to be a Kreutz sungrazer of significant size. The comet was designated C/2011 W3, but everyone called it Lovejoy. When orbital calculations confirmed it was heading into the Sun at an angle that would carry it through the lower corona, the scientific consensus was fairly confident. Objects of that size had not been observed surviving such a passage. The prediction, stated plainly by multiple researchers, was that Comet Lovejoy would not come out the other side. It would be consumed. Solar observatories tracked the comet as it approached. SOHO's coronagraph watched it disappear behind the solar disk on December 16, 2011. The imagery was remarkable, a bright object trailing an enormous tail streaking toward the Sun like a lit match thrown at a bonfire. And then it was gone, behind the Sun, and everyone waited. It came back out. Comet Lovejoy emerged on the far side of the Sun, still visible, still leaving a tail, although the tail was now disconnected and the comet was clearly a shadow of what it had been on approach. Scientists later described it as headless. The nucleus had been devastated. Most of its material had been stripped away, but it had survived the passage through a region where the temperature was over 1,000,000 Kelvin and the radiation environment was more extreme than anything humans have ever directly observed. It had threaded the needle. What Lovejoy demonstrated was not just that large sungrazers could survive corona passage. It demonstrated something about scale. The comet injected an enormous quantity of material directly into the solar corona during its transit. Trails of plasma were visible in solar imagery for days afterward. The Sun's corona showed structural changes in the wake of the passage. Whether those changes were physically significant in terms of solar activity is debated, but they were detectable. They were real. Lovejoy became the closest observational precedent for what C/2026 A1 might experience on April 4, 2026. The two comets share a family lineage, similar orbital geometry, and comparable evidence for substantial nuclear size based on pre-perihelion brightness. The differences are also significant. A1 appears to have been detected earlier and at higher brightness than Lovejoy was at comparable distances, which some researchers interpret as evidence of a larger or more active nucleus. If A1 behaves like Lovejoy, the world gets a spectacular solar event that delights astronomers and produces no consequences for anyone outside the research community. If A1 is substantially larger than Lovejoy, it injects more material, perturbs more magnetic structures, and the already difficult question of comet-corona interaction becomes even harder to dismiss. There is a layer of physics underneath all of this that most discussions skip past, because it involves concepts from plasma physics that are rarely explained to general audiences. It involves a theory proposed by one of the most brilliant and controversial physicists of the 20th century, and it suggests a mechanism by which a comet's interaction with the solar environment could be far more electrically dramatic than standard models predict. Part 8. Critical ionization velocity. Some ideas arrive before the technology needed to test them exists, and spend decades in a state of intellectual limbo. They sit in the literature, cited occasionally, debated politely at conferences, and never quite resolved because the universe simply has not provided the right natural experiment to settle the argument. That is exactly where this idea has been living for over half a century, and April 4th, 2026 might be the day it finally gets its test. Hannes Alfvén was a Swedish physicist who won the Nobel Prize in Physics in 1970 for his work on magnetohydrodynamics, the study of how electrically conducting fluids behave in magnetic fields. He is one of the founders of plasma physics as a discipline, a field that underpins our understanding of everything from fusion reactors to the behaviour of the solar wind. He is also someone who had a reputation for proposing ideas that mainstream physics found deeply uncomfortable before eventually, sometimes grudgingly, finding them correct. His work on plasma waves, now called Alfvén waves, was dismissed for years before experimental confirmation forced the community to take it seriously. He had a talent for being right before anyone was ready to believe him. He proposed the concept of critical ionization velocity, and it is one of those ideas that is either profoundly important or a beautiful theoretical dead end, depending on whom you ask. The physics community has never fully agreed. The idea has been tested in laboratory settings with mixed results, confirmed in some experiments, questioned in others, and the question of whether it operates meaningfully in large-scale astrophysical environments has remained stubbornly open. Alfvén himself believed it was one of his most important contributions. Others have been less certain. The basic principle is this: when a neutral gas, meaning ordinary unionized atoms moving through space, enters a plasma environment and exceeds a specific velocity threshold, it does not gradually ionize the way you might expect from simple heating. Instead, there is an instability. The interaction between the neutral atoms and the surrounding plasma, mediated by magnetic fields, causes the neutral atoms to ionize suddenly and collectively. The process is self-reinforcing. Once it begins, it accelerates. The energy for this ionization does not come primarily from temperature. It comes from kinetic energy, from the speed of motion itself. The atoms are essentially moving so fast through the magnetized plasma that the collision dynamics tip over into a runaway ionization cascade. Now consider what a sungrazing comet actually is in this context. The comet is a neutral gas factory operating at industrial scale. As the nucleus heats and evaporates during its approach to the sun, it releases enormous quantities of water vapor, carbon dioxide, ammonia, carbon monoxide, and other volatile molecules, all neutral, all moving outward from the nucleus in an expanding cloud that can stretch millions of kilometers. By the time the comet reaches the inner corona at perihelion, it has been releasing this material continuously for weeks, and the rate of release is accelerating exponentially as solar radiation intensifies. As these neutral molecules hit the solar corona, they encounter a plasma environment already at temperatures of millions of Kelvin, already threaded through with magnetic field lines carrying enormous energy, already in a state of complex electromagnetic activity driven by the sun's peak solar cycle. The comet itself is moving at hundreds of kilometers per second relative to the surrounding coronal plasma. Alfvén's theory suggests that under precisely these conditions, the relative velocity between the neutral comet gas and the surrounding plasma could cross the critical threshold and trigger precisely the kind of instability he described decades ago in a theoretical framework that the universe had not yet provided the tools to test. If this happens, the result is not a gradual, gentle injection of comet material into the corona, the way you might imagine water slowly dissolving into a river. It is something categorically different. It is something closer to an electromagnetic event, a large, sudden ionization front propagating outward from the comet's path through the corona. Charged particles slamming into the sun's magnetic field and interacting not gently but abruptly, the way a short circuit interacts with a power grid rather than the way a dimmer switch adjusts a light. The comet's tail would, in this model, carry significant electrical currents along the field lines it follows, potentially forming a direct electromagnetic connection between the comet's path through the corona and active magnetic regions on the solar surface far below. Think about what that means for a moment. Not just a comet vaporizing in the corona, but a comet acting as an electrical conductor, a temporary wire connecting the outer corona to the magnetically loaded active regions closer to the solar surface. The energy stored in those active regions is not the comet's energy. The comet is not supplying it, but a sudden electrical connection between an unstable magnetic region and the corona above it could, in principle, initiate a discharge that the region was already primed to produce. The comet becomes less like a rock thrown into a pond and more like a key turning a lock. Here is the necessary disclaimer stated clearly, because intellectual honesty matters more than a dramatic narrative. This is a theoretical mechanism. It has not been confirmed observationally in the context of sun-grazing comets. No mission has yet captured the kind of detailed plasma and electromagnetic data during a large sungrazer perihelion that would allow researchers to verify or rule out the process. Alfvén's broader theories of plasma physics are well established and experimentally verified in many contexts, from laboratory plasma experiments to observations of the solar wind itself. The specific application of critical ionization velocity to sun-grazer-corona interaction remains firmly in the category of speculative but physically motivated hypothesis. It is the kind of idea that serious scientists discuss in private with genuine interest while remaining careful about the language they use in print, because the difference between a published speculation and a published confirmation is everything in physics. The reason this particular hypothesis matters right now in early 2026 is a convergence that did not exist before. Previous large sungrazers, including Comet Lovejoy in 2011, arrived in an era when our solar observing infrastructure was significantly less capable than it is today. SOHO's coronagraph was watching, but Parker Solar Probe did not exist yet. Solar Orbiter did not exist yet. The Daniel K. Inouye Solar Telescope was not yet operational. The combination of in situ plasma measurement from a spacecraft already inside the inner solar system, high-resolution remote sensing from multiple orbital platforms, and ground-based imaging of unprecedented sharpness creates a net of observation around this event that no previous sungrazer has ever flown through. What makes April 4th genuinely significant, beyond the spectacle of a large comet hitting the solar corona, is that for the first time in the history of solar observation, we may have both an object large enough to produce detectable effects and the instrument sensitive enough to measure those effects in the detail required to say something meaningful. Parker Solar Probe is close to the Sun, measuring plasma properties directly. Solar Orbiter is returning high-resolution imagery of coronal structures. The Daniel K. Inouye Solar Telescope on Earth is producing solar surface images sharp enough to resolve features smaller than a large city. The instruments exist. The event is coming. The data will be collected regardless of what happens. Whether that data confirms Alfvén's half-century-old hypothesis, contradicts it, or simply reveals that the corona is more complex and surprising than either possibility predicted, is a question that will have an answer after April 4th that it does not have today. The timing, however, adds one more variable to this already complicated picture, because the Sun itself is currently in a state that makes every part of this scenario more consequential than it would be in a quiet period. And understanding why that matters requires understanding something about the rhythm the Sun has been keeping for billions of years, a rhythm that right now in 2026 is playing at full volume. Part 9, Solar Maximum, the worst possible timing. The Sun breathes, not literally but magnetically, and the rhythm of that breathing has consequences that reach all the way down to the surface of Earth. It is one of those facts that sounds almost poetic until you start thinking about what it actually means for the 7 billion people who have built their entire civilization on the assumption that the electromagnetic environment around this planet will remain more or less stable. That assumption has been correct for long enough that we stopped questioning it. We probably should not have done that. The solar cycle is an approximately 11-year oscillation in the Sun's magnetic activity. The mechanism driving it involves the Sun's differential rotation, meaning the equator rotates faster than the poles, which gradually winds and tangles the magnetic field lines threading through the solar interior like twisted rubber bands accumulating stress. Over years, that magnetic complexity builds toward a breaking point. The Sun's magnetic field gradually becomes increasingly tangled and energetic, reaches a period of maximum activity where the stored magnetic energy finds countless pathways to release itself. then slowly calms and reorganizes as the field resets toward a simpler configuration. Then the whole process starts again. 11 years roughly, over and over for as long as the Sun has existed. During solar minimum, the surface is relatively quiet. Sunspots are rare, flares are infrequent, CMEs are fewer in number and typically less energetic. If you wanted to send a large sungrazing comet into the solar corona, solar minimum would be the politely considerate time to do it. The Sun would still put on a show, but the background conditions would be calmer, the magnetic environment less loaded, the probability of triggering anything already primed to release considerably lower. During solar maximum, the situation is categorically different. The magnetic field is chaotic in the technical sense of that word, meaning small changes in initial conditions produce large and unpredictable variations in outcome. Active regions cluster on the solar surface in groups, each one a knot of intense magnetic energy that can reconfigure rapidly. Sunspots appear in complex configurations that solar physicists classify by their potential for explosive activity. X-class flares, the most powerful category in the standard classification system, become regular occurrences rather than rare events. Coronal mass ejections launch into space not occasionally, but multiple times per day, a continuous bombardment of the inner solar system with clouds of magnetized plasma moving at speeds between several hundred and several thousand kilometers per second. Solar cycle 25 is the current cycle, and it has done something that forecasters find professionally uncomfortable. It has made them look conservative. Early predictions issued before the cycle began ramping up suggested it would be a moderate cycle, perhaps slightly below the historical average in peak activity. The models were reasonable. They were based on established precursor indicators. They were also wrong in a specific direction. Solar cycle 25 has been running consistently ahead of predictions throughout its entire growth phase, producing more sunspot activity, more significant flares, and more powerful geomagnetic storms than the consensus forecast anticipated. The peak activity period was expected somewhere around 2025 to 2026. We are sitting inside that window right now, at what may be the most active phase of an already overperforming solar cycle. The practical consequences of this have already been felt by people who have never thought about solar physics in their lives. In May of 2024, a sequence of powerful solar storms driven by a cluster of active regions rotating across the solar disk launched a series of CMEs toward Earth in rapid succession. The resulting geomagnetic storm reached the highest classification level on the standard scale. Auroras appeared across the continental United States, across Central Europe, as far south as Mexico, the Caribbean, and North Africa. People who had lived their entire lives at latitudes where auroras essentially a mythological phenomenon stood in their backyards at midnight, watching curtains of green and red and purple light ripple across the sky above them. Social media filled with photographs taken by people who were genuinely uncertain what they were looking at. It was, by any measure, beautiful. It was also a warning dressed in extraordinary colours, because the storm that produced those auroras, dramatic and memorable as it was, did not approach the upper end of what the Sun is capable of producing. It caused some satellite operators to take protective measures. It degraded radio communications in certain frequency bands. It produced the auroral display that millions of people photographed and will remember for the rest of their lives. What it did not do was damage major power grid infrastructure or disable critical satellites. It was, in the vocabulary of space weather researchers, a significant event but not a catastrophic one. For the benchmark of catastrophic, you go back not to 2024 but to July of 2012. A coronal mass ejection erupted from the Sun during that month and blasted outward into the inner solar system. It was one of the most energetic solar eruptions measured in the modern era of space-based observation. The magnetic field configuration of the eruption, the speed of the plasma cloud, the density of the material, all of the parameters that determine how severely a CME affects Earth's magnetosphere were measured and analysed in detail. Scientists who worked through the data concluded it was comparable in magnitude to the Carrington event of 1859, possibly equivalent, possibly exceeding it in some parameters. The cloud of solar plasma missed Earth, not by much, in the scale of orbital mechanics. The difference between that CME and a direct hit on our planet was approximately 9 days. Earth had been in the firing line 9 days earlier and had moved on. The eruption blasted into empty space where our planet had recently been and would not be again for another year. 9 days. The margin between a spectacular scientific observation and a global infrastructure emergency was 9 days of orbital motion. The estimates of what a direct hit would have meant vary depending on assumptions about grid protection levels and geographic distribution of damage, but the range of credible figures runs from $1 to several $1 trillion in infrastructure damage in the United States alone, with comparable or greater losses in other heavily electrified regions. Power grid failures cascading across interconnected networks. Satellite systems damaged or destroyed by the radiation environment. GPS degradation affecting aviation, shipping and financial systems simultaneously. Communication infrastructure disrupted across multiple platforms at once. And critically, the kind of recovery timeline measured not in days but in months or years, because the components most vulnerable to geomagnetic storm damage are precisely the components that take the longest to replace. Now place the comet into this picture and hold it there for a moment. A large Kreutz sungrazer from one of the most historically dramatic comet families in the solar system, arriving during the active phase of an unusually strong solar cycle that has already exceeded its own forecast, diving into a corona that is already magnetically complex, already releasing multiple CMEs per day, already in a state where the difference between a quiet afternoon and an X-class flare is simply a matter of which active region decides to reconfigure its magnetic field in the next few hours. The comet is not arriving in a calm, predictable solar environment, where its effects, if any, can be cleanly isolated and studied. It is arriving in the middle of an ongoing electromagnetic symphony that is already playing at high volume, and it is about to add a new instrument that no one has heard in this particular combination before. The honest assessment requires holding two things simultaneously. The first is that the most probable outcome is that this makes no difference to the Sun's behaviour whatsoever. The Sun continues doing what it was already doing. The comet provides a spectacular display in coronagraph imagery. Solar scientists collect invaluable data on comet corona dynamics. Everyone publishes papers. Nobody outside the research community notices. This is genuinely the most likely scenario, and stating that clearly matters. The second thing to hold simultaneously is that most likely is not the same as certainly. The word most likely is doing considerable work in the previous paragraph, and the infrastructure that would bear the consequences of the alternative scenario was never designed with this specific combination of variables in mind. It was not designed for a Carrington-class event under any circumstances. The addition of a large sungrazer during solar maximum does not change the fundamental vulnerability. It simply adds one more variable to an already complex system in a way that cannot be fully modelled in advance. What happens when the comet arrives will be observed in more detail than any previous solar event of this type. The data will be extraordinary. But the grid that sits underneath all of this, the infrastructure that modern civilization depends on, in ways most people never think about until the lights go off, was built by engineers solving different problems in a different era, and it has never been tested against what the Sun is genuinely capable of producing when everything lines up in the wrong direction at the same time. Part 10, the grid that was never built for space weather. Modern civilization is an electromagnetic organism. Every meaningful function of contemporary life runs on electricity, and electricity moves through infrastructure that was designed by engineers who were thinking about power plants and load balancing and cable losses, not about what happens when the Sun decides to have a bad day. This is not a criticism of those engineers. They were solving the problems in front of them, and they solved them brilliantly. The power grid is one of the most complex and impressive engineering achievements in human history. It is also, from the perspective of space weather, built almost perfectly wrong. To understand why, you need to understand what a geomagnetic storm actually does to the physical world. Not in abstract terms, but in the specific mechanical, unglamorous way that things break when the Sun throws a billion-ton cloud of magnetized plasma at Earth's magnetic field. Geomagnetic storms work through a mechanism that is elegantly simple and practically devastating. When a coronal mass ejection strikes Earth's magnetic field, the field does not simply absorb the impact and hold steady. It fluctuates, it oscillates, it compresses on the sunward side and stretches on the far side, and rings like a struck bell across its entire structure. A changing magnetic field, as any physicist will tell you, induces electric currents in any nearby conductor. This is not an exotic or unusual effect. It is the same fundamental principle that makes electric generators work, the same principle behind every motor in every appliance in your home. Move a magnetic field near a conductor and current flows. It is one of the most reliable relationships in all of physics. The problem is that Earth's surface is covered with extremely long conductors that nobody put there for electromagnetic purposes, but which serve that function regardless. Power transmission lines stretching hundreds and thousands of kilometers across continents act as enormous antennas for geomagnetically induced currents. The longer the conductor, the more current gets induced. A transmission line running from one end of a continent to the other is, from the perspective of a fluctuating magnetic field, an almost ideal antenna. The currents that flow through it during a severe geomagnetic storm are not the alternating currents the grid was designed to carry. They are direct currents, slow and persistent, flowing into the grid from the ground up through the neutral grounding points of the most critical components in the entire system. Those components are the high voltage transformers, and understanding what makes them uniquely vulnerable requires spending a moment with what they actually do and what they actually are. A high voltage transformer is the device that steps electrical power up to the extreme voltages needed for long distance transmission, sometimes hundreds of thousands of volts, and then steps it back down for local distribution. Without transformers, the modern power grid as it exists simply cannot function. They are not a component that can be bypassed or worked around. They are the grid, in a fundamental sense. They are also among the most difficult pieces of electrical equipment on Earth to replace. Each one is custom engineered for its specific location in the grid, its specific voltage requirements, its specific load characteristics. They are not mass-produced items sitting on shelves somewhere. They are built to order and they are large. We're talking about devices that weigh between 100 and 800 tons. Moving one requires specialized heavy transport equipment, often custom-built railcars or multi-axle road transporters, and routes planned months in advance to ensure bridges and roads can handle the load. Manufacturing them requires specialized facilities, specialized steel alloys, specialized winding equipment, and skilled labor that is not abundantly available. Lead times from order to delivery, under normal peacetime commercial conditions with no competing urgent demand, run from 12 months to 30 months. There is no strategic reserve of spare high-voltage transformers. There is no warehouse somewhere filled with backup units ready to be deployed after a grid emergency, the way there are strategic petroleum reserves or emergency food stockpiles. The supply chain for these devices was optimized for the normal replacement schedule of aging equipment, not for the simultaneous failure of dozens or hundreds of units across multiple countries in a single event. The just-in-time manufacturing logic that makes the global economy efficient in normal conditions becomes a critical vulnerability when the abnormal arrives without warning. A severe geomagnetic storm capable of inducing currents strong enough to saturate and thermally damage multiple transformers simultaneously would not produce the kind of power outage that people have experience with. A blackout from a winter storm or a grid management failure lasts hours, sometimes days. Crews mobilized, damages located, repairs are made, power is restored. People are inconvenienced. Some suffer, particularly the elderly and the ill. But the recovery timeline is measured in days at most. The infrastructure to restore power exists and can be deployed quickly because the damage is mechanical and the replacement parts are available. A transformer failure event driven by a Carrington-scale geomagnetic storm operates on a completely different timeline. The blackout would be measured in months, potentially much longer in the most severely affected regions. Not because the will or the workforce to repair it would be absent, but because the replacement components would not exist in sufficient quantity to be installed. You cannot repair or replace a custom-built 400-ton transformer in weeks. You cannot manufacture 10 of them simultaneously when your factory was built to produce 3 per year under normal conditions. The timeline is dictated by physics, metallurgy, and supply chain reality, not by urgency or political will. The people most at risk in that scenario are not difficult to identify. They are not the people who miss a day of work or lose a refrigerator full of groceries. They are the patients in hospitals whose life support systems run on electricity, in regions where backup generators would exhaust their fuel supplies long before grid power returned. They are the people in climates where heating or cooling is not a comfort, but a survival requirement, where extended loss of power during winter or summer becomes a direct threat to life. They are the communities dependent on electrically pumped water systems, where taps run dry within days of a grid failure and the logistics of alternative water supply at municipal scale quickly exceed available resources. The vulnerability is not evenly distributed, but it is widespread, and it reaches into populations that have no particular awareness of space weather and no reason to have planned for it. The satellite layer of this problem operates in parallel and compounds it. During strong geomagnetic storms, the heating of Earth's upper atmosphere by incoming particle radiation causes it to expand outward. The atmosphere becomes physically larger. Satellites in low Earth orbit, which were designed and positioned based on the atmospheric density profile under normal conditions, suddenly find themselves moving through air that is measurably thicker than expected. The drag increases. The orbits decay faster. For satellites with fuel reserves, this can be corrected with orbital adjustment burns. For satellites without sufficient fuel margin, or for constellations of small satellites not designed with this contingency in mind, the consequences can mean loss of the asset entirely. Beyond orbital decay, the radiation environment during a severe geomagnetic storm can damage satellite electronics directly. Solar cells degrade. Onboard computers experience single event upsets, where individual memory bits are flipped by energetic particles passing through the chip. In extreme cases, this causes permanent damage to systems that cannot be repaired from the ground. The GPS constellation, which underpins navigation for aviation, maritime shipping, precision agriculture, financial transaction, timestamping, and emergency services simultaneously, operates in medium Earth orbit where the radiation environment during a major storm is particularly severe. Signal degradation during the ionospheric disturbance accompanying a geomagnetic storm is well documented and can reduce GPS accuracy from meters to kilometers, rendering precision-dependent systems unreliable at exactly the moment when reliable navigation and communication would be most needed. None of this is hypothetical in the sense of being imaginary or speculative. Every effect described here has been observed at smaller scales during storms that have already occurred during the modern era. The 1989 Quebec blackout, caused by a geomagnetic storm that destroyed transformers and left 6 million people without power for 9 hours, demonstrated the grid vulnerability with real consequences in a real city. The 2003 Halloween storms caused aviation rerouting, satellite anomalies, and power disturbances across multiple continents. The May 2024 storms degraded GPS signals, affected satellite operations, and drove auroras to latitudes that had not seen them in living memory. The data from these real events, combined with the physics of what a significantly stronger storm would do to the same infrastructure, produces estimates that are not modelling exercises. They're extrapolations grounded in observed cause and effect relationships. Governments and power companies in several countries have taken this seriously enough to begin developing mitigation strategies. Grid-level capacitors that can block geomagnetically induced currents from reaching transformer neutral points have been developed and deployed in limited numbers. Early warning systems using solar observatory data to give grid operators advance notice of incoming CMEs have been established, providing windows of anywhere from 15 minutes to several hours depending on storm speed. Some utilities have begun stockpiling critical spare components and developing rapid response protocols for space weather events. These efforts are real, they are meaningful, and they represent genuine progress compared to where the conversation was 20 years ago. They are also incomplete in ways that matter. Coverage is uneven across different countries and different grid operators. The warning windows provided by current solar monitoring, while valuable, are short, relative to the time needed to fully protect a large interconnected grid. The stockpiling of spare transformers has improved, but remains far below what a worst-case scenario would require, and the systems have never been tested against an actual Carrington-scale event, because no such event has occurred since any of these protective measures were installed. The conversation around space weather preparedness has been growing louder in policy circles for years, moving slowly from the domain of specialist researchers into the awareness of infrastructure planners, insurance actuaries, and national security analysts. What arrives on April 4th may contribute nothing new to that conversation, or it may contribute something that changes its urgency in ways that are difficult to predict from this side of the date. Either way, the question of whether our civilization is adequately prepared for what the sun is capable of doing remains open in a way that deserves more attention than it currently receives from the people who would bear the consequences of the answer. Part 11. the asteroid that changed planetary defense. On September 26, 2022, a spacecraft traveling at approximately 6.1 kilometers per second hit an asteroid approximately 160 meters in diameter, and humanity changed its relationship with the universe. Not metaphorically, not philosophically. In a direct, measurable, physically verifiable way, our species demonstrated for the first time in 4.5 billion years of Earth's history that we are not simply passengers on this rock, subject to whatever the solar system decides to throw at us. We can push back. It turns out that matters enormously, and not just for the reason you might immediately think. The DART mission, which stands for Double Asteroid Redirection Test, was the first deliberate test of planetary defense technology in history. The concept had been discussed in scientific literature and policy documents for decades. The basic physics were well understood. A spacecraft with enough mass and velocity, striking an asteroid at the right angle, would transfer momentum and alter the object's trajectory. The mathematics were not in serious dispute. What had never been demonstrated was whether the engineering could actually be executed, whether the targeting precision required could be achieved across millions of kilometers of space, and whether the real-world outcome would match the theoretical prediction. Science requires more than elegant equations. It requires evidence. The target was Dimorphos, a small moon orbiting a larger asteroid called Didymos, a gravitationally bound pair that together form what astronomers call a binary asteroid system. Neither object posed any actual threat to Earth. That was deliberate. The selection of a non-threatening target was a conscious choice to ensure that even if something went unexpectedly wrong with the experiment, no one had inadvertently redirected a hazardous object toward the planet they were trying to protect. Dimorphos and Didymos were a perfect natural laboratory, two objects whose orbital relationship could be precisely measured before and after the impact, giving researchers a clean way to quantify exactly how much the collision changed things. The answer was unambiguous, and it was better than expected, which in science is one of the most exciting phrases you can encounter. Not only did DART successfully change the orbit of Dimorphos around Didymos, it changed it significantly more than the pre-mission predictions had anticipated. The spacecraft's kinetic impact transferred momentum directly into the asteroid, but that was only part of the story. The collision also excavated an enormous quantity of material from Dimorphos' surface, launching it outward into space as a plume of debris that stretched thousands of kilometers and was photographed by telescopes around the world. That ejected material provided a recoil effect, like the kick of a gun, that amplified the deflection well beyond what the spacecraft's mass alone would have produced. The orbital period of Dimorphos around Didymos changed by over 32 minutes. The pre-mission minimum success threshold, the number that would have counted as proof of concept and allowed the team to declare victory, was a change of 73 seconds. They achieved more than 25 times that minimum threshold. The physics worked, and it worked generously. The engineers and scientists who built and operated DART had succeeded, not just in demonstrating the concept, but in demonstrating it with a margin that provided genuine confidence for future applications. The follow-up mission, ESA's Hera spacecraft, launched in October of 2024 and is currently travelling toward the Didymos system. When it arrives, it will do something DART could not do from the outside. It will characterise the impact site in detail, measuring the shape of the crater, the structure of the subsurface material exposed by the collision, the precise mass distribution of Dimorphos, and the exact changes in the asteroid's rotation and orbit. This data matters because the effectiveness of a kinetic impactor depends heavily on the internal structure of the target. A loose rubble pile, which many small asteroids are believed to be, responds differently to impact than a solid monolithic rock. Hera's measurements will ground truth the models that planetary defense planners use to design future missions, replacing assumptions with measurements and predictions with calibrated calculations. The current catalogue of known near-Earth objects, meaning asteroids and comets, whose orbits bring them into the vicinity of Earth's orbital path, now numbers in the 30,000 range. That number grows every month as survey programs improve their sensitivity and sky coverage. The Planetary Defense Coordination Office at NASA actively tracks all of these objects, running orbital calculations continuously to identify any that have non-negligible probabilities of intersecting Earth's orbit within the next century. The vast majority have impact probabilities that round to zero for the foreseeable future. A small number require ongoing monitoring, An even smaller number occasionally generate headlines when preliminary calculations suggest elevated risk, before additional observations refine the orbit and typically reduce the probability back towards zero. The infrastructure supporting this effort, spanning multiple ground-based survey telescopes, dedicated tracking facilities, international coordination networks, and sophisticated orbital modelling software, represents an investment in planetary awareness that would have been genuinely unimaginable to astronomers working 50 years ago. In the 1970s, the Near-Earth Object Catalogue contained a few hundred known objects. The idea of tracking 30,000 of them in real time with orbital predictions extending decades into the future would have seemed like science fiction to researchers working with the computational and observational tools of that era. The significance of all of this extends considerably beyond asteroids and the specific engineering achievement of DART. What the mission demonstrated is a broader capability that represents a genuine threshold in the history of this planet. For the first time in the entire span of complex life on Earth, a species inhabiting this planet has the demonstrated ability to deliberately interact with the orbital dynamics of the solar neighbourhood. We are not purely passive observers of events unfolding around us according to physical laws we can calculate but cannot influence. We can, under the right circumstances, with sufficient warning time and resources, change the outcome. That is a new thing. It has never been true before in 4.5 billion years of Earth's existence, and it became true on September 26, 2022, when a refrigerator-sized spacecraft hit a rock 160 meters across and moved it. The philosophical implications of that threshold are worth sitting with for a moment, because they tend to get lost in the technical details. Every mass extinction in Earth's history, every catastrophic impact event that reshaped the biosphere, every rock that fell from space and ended species or altered the course of evolution, happened to a planet that had no ability to respond. The dinosaurs, to use the most familiar example, had no option. The impactor arrived, the consequences unfolded, and the history of life on Earth changed irrevocably, without any possibility of intervention. For the first time, that is no longer unconditionally true. The intervention capability is limited, it is dependent on sufficient warning time, and it requires resources and coordination that are not guaranteed. But it exists. The option is on the table in a way it never was before. The irony embedded in this achievement, and it is a real irony worth naming clearly, is that the category of objects for which this capability is most limited is precisely the category that includes C/2026A1. Comets, particularly those arriving from the outer solar system on highly elliptical orbits, represent the remaining frontier of the planetary defense challenge in a way that is fundamentally different from the near-Earth asteroid problem. The difference comes down to warning time, and warning time is everything in planetary defense. A near-Earth asteroid on a potentially hazardous orbit can be detected, tracked, and characterized years or decades before any projected impact date. The orbital period of such an object is short enough that it makes multiple passes through the inner solar system, each one providing opportunities for additional observation, refined orbital calculations, and mission planning. The warning time for a well-catalogued near-Earth asteroid could be decades, which is sufficient for multiple mission attempts using current or near-future technology. A long-period comet arriving from the outer solar system operates on a completely different timeline. These objects spend most of their existence in the far reaches of the solar system, beyond the detection threshold of current survey telescopes, invisible against the background of space until they begin their inward journey, and start developing the coma of gas and dust that makes them visible. By the time a long-period comet is detected, it may already be inside the orbit of Jupiter, leaving months rather than years or decades before closest approach to the inner solar system. The window for any kind of deflection mission in that scenario is narrow to the point of being nearly non-existent with current technology. You cannot design, build, launch, and intercept a comet in 6 months using hardware that does not yet exist. C/2026A1 is a Kreutz sungrazer, not a direct Earth impactor, and its perihelion trajectory carries it toward the Sun rather than toward our planet. The planetary defense challenge it poses is not one of deflection, but its arrival illustrates with uncomfortable clarity how the detection and response timeline for transient solar system visitors can compress rapidly, and how the infrastructure we have built for watching the sky, impressive as it is, still has boundaries that the universe does not respect. The story of how those boundaries are being pushed outward and what lies just beyond them began with the detection in 2017 that rewrote what astronomers thought they knew about what passes through our solar neighbourhood. Part 12. Interstellar visitors are becoming common. In October of 2017, astronomers detected an object moving through our solar system that had not formed here. That sentence, stated plainly, does not fully convey how significant the moment was. Every object ever previously observed in our solar system, every planet, every moon, every asteroid, every comet, every grain of dust swept up by a spacecraft instrument, had originated in the same cloud of gas and dust that collapsed to form the Sun 4.5 billion years ago. Everything was local, everything was family. And then, without announcement or ceremony, something arrived from somewhere else entirely, and the solar system was suddenly a less private place. Oumuamua, named using a Hawaiian term carrying the sense of a messenger from far away arriving first, was moving too fast to be gravitationally bound to the Sun. This is the critical diagnostic. Objects that form in our solar system, regardless of how elongated or unusual their orbits might be, are bound to the Sun by gravity. Their paths are ellipses, closed curves that bring them back around again on timescales, ranging from years to millions of years. Oumuamua's path was hyperbolic. It was an open curve, a trajectory that passed through the inner solar system and continued outward without ever returning, carrying the object back into interstellar space on a one-way journey that had begun somewhere we cannot identify and will end somewhere we will never reach. The strangeness did not stop at the trajectory. Oumuamua was elongated in a way that defied easy categorization. Estimates of its shape, derived from the way its brightness varied as it rotated, suggested an aspect ratio somewhere between 5:1 and 10:1, meaning it was anywhere from 5 to 10 times longer than it was wide. No solar system object of comparable size has ever been observed with proportions anywhere near that extreme. Comets are roughly spherical or gently irregular. Asteroids vary, but cluster around shapes that reflect the physics of accretion and collision. Oumuamua looked like something that had been stretched, or grown, or formed under conditions that our solar system simply does not replicate. Its rotation was tumbling rather than spinning cleanly around a single axis, suggesting it had experienced some kind of disruptive event in its history, a collision perhaps, or tidal stress from a close encounter with a massive object somewhere in its interstellar journey. And then there was the acceleration. As Oumuamua moved away from the Sun after its closest approach, it was accelerating slightly faster than solar gravity and radiation pressure alone could account for. The discrepancy was small but real, confirmed by multiple independent analyses of the tracking data. Something was pushing it, gently but measurably, beyond what physics predicted for a passive inert object. The explanations proposed for that anomalous acceleration range from the mundane to the genuinely exotic. Outgassing, the release of volatile material from a comet-like nucleus heated by solar radiation, was the most conventional explanation, but no cometary activity, no coma, no dust tail was ever detected despite sensitive searches. A thin, flat geometry that would respond to radiation pressure more strongly than a compact object was proposed. One researcher, whose name you may recognise, suggested the possibility of an artificial origin, a proposal that generated enormous public attention and considerably more cautious responses from the broader astronomical community. The honest answer, stated without embarrassment, is that no single explanation fully satisfied all of the observational constraints simultaneously. Oumuamua remains, as of the current state of knowledge, genuinely unexplained in certain details. That is not a comfortable place for science to sit, but it is where the data leaves us. Then in 2019, before the debate over Oumuamua had settled, astronomers found Comet Borisov, the second confirmed interstellar object in 2 years, after none in all of recorded human history. Borisov was in many ways the more reassuring of the two visitors. It behaved recognizably like a comet. It developed a coma. It showed spectroscopic signatures of water vapor and carbon monoxide, familiar cometary molecules. Its interstellar origin was unmistakable from the speed and curvature of its trajectory, but its physical behavior was something astronomers had seen before, just never from so far away. Borisov was, in a sense, a comet from another star that looked enough like comets from our own star to feel almost familiar. Almost. The fact that two interstellar objects were detected within 2 years of each other, after 0 confirmed detections in all previous astronomical history, demands an explanation, and the explanation is not that interstellar objects suddenly started visiting our solar system in 2017. The solar system has almost certainly been receiving interstellar visitors continuously throughout its entire history. Rocky debris, icy fragments, and dust from other planetary systems drift through the galaxy constantly, scattered by gravitational interactions, ejected by forming planets, launched into interstellar space by stellar encounters and supernova shockwaves. The interstellar medium is not empty. It is populated by material from billions of stellar systems accumulated over billions of years of galactic history. What changed in 2017 was not the arrival rate of interstellar objects. What changed was us. The survey programs that detected Oumuamua and Borisov represent a generation of astronomical technology that simply did not exist a decade earlier. Automated wide-field telescopes running continuously, scanning large fractions of the sky repeatedly, processing the resulting data through algorithmic pipelines capable of identifying moving objects against a background of billions of fixed stars. All of this infrastructure was built and deployed and refined over the course of the 2000s and early 2010s. By 2017, it had reached the sensitivity threshold required to catch a fast-moving interstellar object during its brief transit through the inner solar system. The same infrastructure, the same generation of survey technology, discovered C/2026A1 earlier and at greater distance than any previous Kreutz sungrazer. The comet story and the interstellar object story are products of the same revolution in how we watch the sky. The Vera C. Rubin Observatory in Chile represents the next step in that revolution, and the step is a large one. The observatory's primary mirror spans 8.4 meters, and its camera is the largest digital camera ever built for astronomical use, covering an area of sky roughly 40 times the size of the full moon in a single exposure. Its design is optimized for the Legacy Survey of Space and Time, a 10-year program that will image the entire visible southern sky repeatedly, returning to each patch of sky every few nights, and building up a time domain record of the universe that no previous facility has approached. The cadence and depth of this survey are specifically designed to catch transient objects, things that move, things that appear and disappear, things that change brightness on timescales from seconds to years. Estimates from researchers who have modelled the expected detection rate suggest that once Rubin is operating at full capacity, we may discover dozens of interstellar objects per decade. Not one every few years, which is the current rate, but multiple per year, each one a new data point in what will become a statistical sample large enough to draw real conclusions about the population of interstellar material passing through our solar neighbourhood. The difference between one example and a statistical sample is the difference between a curiosity and a scientific field. These objects are not curiosities in the dismissive sense of that word. They are, in a meaningful physical sense, samples from other planetary systems delivered to our doorstep by the dynamics of the galaxy. The chemical composition of an interstellar comet reflects the conditions in the protoplanetary disk where it formed, potentially around a star with different elemental abundances than our Sun, at a different distance from its parent star, in a disk with different temperature and pressure gradients. The organic molecules carried by such an object might have histories tracing back not just to their parent planetary system, but to the interstellar molecular cloud from which that system condensed, carrying isotopic and chemical signatures that encode information about conditions billions of years ago in regions of the galaxy we will never physically visit. Every interstellar visitor is, in this sense, a message in a bottle. The bottle has travelled an unimaginable distance. The message is written in chemistry and physics rather than language. Reading it requires instruments and techniques that are still being developed, but the messages are arriving, and we are finally building the capability to intercept them. The infrastructure being constructed to detect and study interstellar objects is not separate from the infrastructure built to watch for hazards, track solar activity, and monitor transient events throughout the solar system. It is the same infrastructure. The same telescopes serve multiple purposes simultaneously. The same algorithms that flag a fast-moving interstellar object also flag an unusual comet brightening faster than expected in the outer solar system. The same global coordination networks that share planetary defense data also distribute solar weather alerts and comet discovery announcements. The universe has not become more active or more dramatic in recent years. It has been doing what it has always done. What has changed is that we have finally built sensors sensitive enough to hear it properly, and what we are hearing is considerably more complex and eventful than the quieter instruments of previous generations suggested. Some of the most sensitive instruments ever aimed at the sky are now pointed at our own sun, positioned closer to it than any human technology has previously achieved, returning data of a quality that would have seemed implausible to solar physicists working even 20 years ago. And on April 4th, 2026, all of that capability converges on a single event that has been building since the early weeks of the year, an event that the next generation of solar observatories was, almost by coincidence of timing, perfectly positioned to witness in full. Part 13, the next generation solar observatories. There is a spacecraft currently orbiting the Sun closer than Mercury, inside the orbit of the innermost planet, travelling fast enough to nearly match the Sun's rotation and hold position over specific active regions. If you find that sentence difficult to fully absorb, you are having the appropriate reaction. Mercury is already so close to the Sun that its surface temperature swings between negative 180 degrees Celsius at night and over 400 degrees Celsius during the day, a range so extreme that the planet has essentially no stable chemistry on its surface. Parker Solar Probe is inside that orbit. It is operating in an environment that, by any intuitive measure, a spacecraft simply should not be able to survive, and it has been doing so repeatedly, successfully and scientifically productively since 2018. Parker Solar Probe launched in August of 2018, carrying a mission profile that required solving an engineering problem with no clean precedent. Getting close to the Sun is not simply a matter of pointing a rocket inward and accelerating. The Sun sits at the bottom of an enormous gravitational well, and objects falling toward it naturally accelerate to speeds that make orbital insertion extremely difficult. To slow down enough to enter a close solar orbit requires shedding enormous amounts of orbital energy, which the mission accomplished through a series of gravity assist maneuvers using Venus, 7 of them across the mission timeline, each one bending the spacecraft's trajectory and lowering its perihelion incrementally. The orbital mechanics alone represent a masterpiece of trajectory planning that took years to design. The thermal engineering is where the mission becomes genuinely extraordinary. The heat shield protecting Parker Solar Probe is a structure called the Thermal Protection System, a circular shield 4.5 feet in diameter and about 4.5 inches thick, constructed from a carbon foam core sandwiched between 2 carbon fibre face sheets and coated on the sun-facing side with a white ceramic paint. The sunlit face of this shield reaches temperatures exceeding 1300 degrees Celsius during the closest solar passes. The instruments mounted in the shield's shadow, separated from that temperature by less than a metre of engineered material, operate near room temperature. The engineering margin between a functioning spacecraft and a molten one is maintained by a structure you could lift with one hand, doing its job millions of kilometres from any possibility of repair. The scientific return from this audacity has been proportional to the risk. Parker Solar Probe has made multiple passes through the actual solar corona, not observing it from a safe distance, but physically flying through it, collecting plasma samples, measuring magnetic field strengths and orientations, recording the velocities and compositions of solar wind particles at their point of origin, rather than after they have travelled millions of kilometres and evolved beyond easy interpretation. The data has already overturned several assumptions about how the solar wind is generated and accelerated, revealing that the process involves impulsive events called switchbacks, sudden reversals in the magnetic field direction of the solar wind that were not predicted by the leading models and whose origin and significance are still being actively investigated. Every orbital pass brings Parker closer to the Sun than the previous one, and the mission is approaching its designed endpoint. The final planned perihelion pass will bring the spacecraft within approximately 6.2 million kilometres of the Sun's photosphere, the visible surface, which places it well inside the corona where the plasma environment is densest and most dynamic. By the time April 2026 arrives, Parker Solar Probe will be positioned in the inner solar system during precisely the period when C/2026 A1 is making its final approach and perihelion passage. The proximity of the spacecraft to the event will allow plasma measurements of comet-corona interaction at a resolution and detail that no instrument has ever achieved, not because the mission was designed with this comet in mind, but because the timeline of the mission and the arrival of the comet happened to coincide in a way that planetary scientists would describe as fortunate. Solar Orbiter approaches the Sun from a perspective that complements Parker in ways that make the combination of the two missions significantly more powerful than either would be alone. Launched in February of 2020 as a joint mission between the European Space Agency and NASA, Solar Orbiter carries a suite of both in-situ instruments measuring the plasma environment around the spacecraft and remote sensing instruments imaging the Sun from a variety of distances and wavelengths. Its orbital plane is being gradually tilted away from the ecliptic, the flat plane in which Earth and most of the planets orbit, through a series of gravity assist maneuvers, using Venus in a deliberate echo of the strategy used by Parker. The reason for this tilt is access to the solar poles, and the reason the solar poles matter is magnetic. The Sun's polar magnetic field plays a critical role in organising the large-scale structure of the heliosphere, the bubble of a solar influence extending far beyond the outer planets. The polar field strength at solar minimum serves as a precursor for the activity level of the next solar cycle, which is why forecasters pay close attention to it. But the poles are essentially invisible from Earth's vantage point in the ecliptic plane. You cannot image the North Pole of the Sun from Earth any more than you could photograph the North Pole of a basketball by looking at it from the equatorial plane. Solar Orbiter's tilted orbit is progressively opening up that view, and the images and measurements it is returning from higher solar latitudes are already filling in gaps in the three-dimensional picture of solar magnetic structure that Earth-bound observations could never address. The remote sensing instruments on Solar Orbiter have also produced discoveries that were not anticipated when the mission was designed. Among the most intriguing are structures now informally called campfires, small brightenings in the extreme ultraviolet images of the solar surface covering spatial scales of a few hundred kilometers and lasting for tens of seconds to a few minutes. They appear to be miniature versions of the larger flare and reconnection events seen in active regions, operating at the smaller scales the instrument can resolve and potentially continuing to even smaller scales below the detection threshold. Their relevance to the coronal heating mystery, the paradox of the corona being so much hotter than the surface below it, is being actively investigated, with some researchers proposing that the cumulative energy input from countless tiny reconnection events throughout the corona could account for the temperature discrepancy that has puzzled physicists for decades. On the ground, the Daniel K. Inouye Solar Telescope on the island of Maui in Hawaii represents what happens when the ground-based solar observation community receives the resources to build something truly ambitious. Its primary mirror spans 4 meters, making it the largest solar telescope in the world by a significant margin, and its location at high altitude on Haleakala provides atmospheric conditions that, combined with its adaptive optic systems, allow it to correct for atmospheric blurring in real time with a sophistication that previous solar telescopes could not match. The result is solar imagery of a quality that genuinely startles people seeing it for the first time. The images returned by Inouye show the solar surface not as a smooth glowing disk or even as a textured surface with visible sunspots, but as a seething, turbulent, constantly reorganizing cellular structure. Each convection cell, called a granule, represents a column of hot plasma rising from below, spreading laterally as it cools and sinking back down along the darker boundaries between cells. The granules are roughly the size of a large country on Earth, and they turn over completely in about 10 minutes. The surface of the Sun is, in this imagery, revealed as a dynamic system operating on timescales and spatial scales that connect directly to the magnetic field evolution, driving everything from small campfires to the largest X-class flares. The magnetic field information embedded in the light from this surface, measurable through a technique called spectropolarimetry that analyses the polarization of spectral lines, provides data about field strength and orientation that feeds directly into models of where and when eruptions are likely to occur. Together, Parker Solar Probe, Solar Orbiter, and the Daniel K. Inouye Solar Telescope form an observational network around the Sun that represents the collective aspiration of solar physics as a field, finally realized in hardware. The combination of direct plasma measurement from inside the corona, multi-wavelength remote sensing from a spacecraft with access to solar latitudes invisible from Earth, and ground-based imaging of unprecedented resolution creates something that no single instrument could provide alone. It creates context. It creates the ability to connect a measurement of particle properties at one location with an image of the magnetic structure at the source region, to trace the chain of cause and effect from the surface through the corona and into the solar wind with a continuity of observation that previous generations of researchers could only approximate. When C/2026A1 arrives at perihelion on April 4th, this entire network will be active, calibrated, and pointed at the event. The comet will be the most extensively observed sungrazer in history by a margin that is not close. Every photon of data that the instruments can collect will be collected. Every plasma measurement, every magnetic field reading, every high-resolution image of the corona before, during, and after perihelion will be recorded and archived. Whatever happens, the scientific record of this event will be complete in a way that no previous sungrazer encounter has been, and the analysis of that record will occupy researchers for years. Making sense of that volume of data will not happen on purely human timescales, and the transformation of astronomy by the tools now being applied to exactly this kind of challenge is itself a story worth telling in full. Part 14. Artificial Intelligence is Transforming Astronomy. Modern telescopes do not just collect light, they generate avalanches of data that no human team could meaningfully analyse without help, and the scale of what we are talking about is worth making concrete before moving past it, because the numbers involved in modern astronomical data production sit in a range that the human brain is genuinely not equipped to intuitively grasp. The Vera C. Rubin Observatory, currently in its final commissioning phase in Chile, is expected, when fully operational, to generate approximately 15 terabytes of data per night. Every night, without interruption, for 10 years. To put that in terms that connect to everyday experience, 15 terabytes is roughly equivalent to the text content of about 15 million books, generated every single night. The full legacy survey of space and time that Rubin is designed to conduct will ultimately produce a catalogue containing approximately 20 billion galaxies and a comparable number of other astronomical sources, including stars, transient events, moving objects, and phenomena that do not yet have names because they have not yet been discovered. If you attempted to print the complete dataset on standard paper at normal document density, the resulting stack would extend from the surface of Earth to the Moon and back multiple times over. This is not a metaphor for a large amount of data. It is a description of a specific quantity that happens to be so large that physical metaphors are the only way to make it feel real. Human astronomers are deeply and irreplaceably involved in designing the scientific program, formulating the questions, interpreting the results, and making the judgments that require contextual understanding and creative inference. But the initial processing of raw telescope data into scientifically usable form, the classification of detected objects, the identification of anomalies that deviate from expected behaviour, the flagging of transient events that require rapid follow-up, none of this happens through human inspection of individual images. It happens through automated computational pipelines, running machine learning algorithms trained on datasets containing hundreds of millions of labelled examples. The human role in modern big sky astronomy increasingly resembles the role of an architect rather than a bricklayer. The vision, the design, and the final interpretation are human. The execution of the detailed work at scale is not. This is not a new development in astronomy broadly, but its application to solar physics and space weather science specifically is newer, and in some ways more urgently consequential than its application to extragalactic survey astronomy. Knowing the precise distance to a galaxy cluster 10 billion light-years away is scientifically important on timescales of decades and centuries. Knowing whether a solar active region is likely to produce an X-class flare in the next 12 hours is important on timescales that affect decisions being made right now by power grid operators, satellite controllers, airline dispatchers, and military communication managers. Solar flare prediction is one of the most commercially and strategically valuable unsolved problems in operational space weather science, and the reason it remains unsolved despite decades of effort is not lack of data. It is the complexity of the physical system. Solar active regions contain magnetic field configurations whose stability properties depend on details of the three-dimensional field structure that surface imagery can only partially reveal. The same sunspot group configuration that erupts catastrophically on one solar cycle might remain quiet through an entire rotation on another, because the subsurface field geometry differs in ways that surface observations cannot directly measure. Traditional forecasting methods handle this irreducible complexity by classifying active regions into categories based on observable surface properties and applying historical eruption rates for each category. The approach is essentially statistical in a way that provides probabilities but limited precision. Machine learning systems applied to this problem operate differently, and the difference matters. Rather than working from human-defined categories and manually extracted features, these systems learn directly from the raw data, identifying patterns in solar imagery and magnetogram sequences that correlate with subsequent flare occurrence, without being told in advance what those patterns represent physically. Trained on decades of solar observations matched against flare event records, the best current machine learning flare prediction systems are achieving accuracy levels that exceed traditional methods across multiple performance metrics, with the most significant improvements appearing precisely in the prediction of the highest magnitude flares, the X-class events, where the consequences of a missed prediction are most severe, and the value of accurate forecasting is highest. The practical implications of this improvement are not abstract. If a power grid operator in a vulnerable region receives a high-confidence warning 12 hours before a major geomagnetic storm, that operator has options. High-voltage transformers can be temporarily taken offline and disconnected from the grid, eliminating the pathway through which geomagnetically induced currents would otherwise flow into their neutral grounding points. The grid operates in a degraded but protected mode during the storm window, and full service is restored once the threat has passed. Sensitive satellite instruments can be placed in protective modes that reduce their exposure to energetic particle radiation. Spacecraft operators can adjust orientations to minimize cross-sectional area exposed to incoming solar wind. Airlines can reroute polar flights that would otherwise pass through regions of intense particle radiation and radio communication blackout. A few hours of reliable warning converts what would otherwise be a potential catastrophe into a manageable inconvenience. The difference between those two outcomes is not engineering or infrastructure investment, though those matter enormously. It is information delivered with sufficient accuracy and sufficient lead time to enable action. Machine learning is improving the quality and reliability of that information in ways that traditional physics-based models have struggled to match, not because the physics-based models are wrong, but because the system is complex enough that data-driven pattern recognition captures predictive signal that analytical models currently cannot fully encode. The application of these tools extends beyond flare prediction into the broader challenge of tracking and characterizing the transient object population of the solar system. Automated systems now scan the data streams from major survey telescopes continuously, applying algorithms trained to identify moving objects against a background of fixed stars to classify detected objects by their orbital characteristics, to estimate brightness and activity levels, and to flag anything that deviates from the expected behavior of known object classes. The detection pipeline for C/2026A1 processed the initial discovery through multiple layers of automated validation before a human astronomer confirmed the result and the object entered the official catalogue. The efficiency of this process from initial detection to confirmed discovery has compressed from weeks or months to hours over the course of the past decade, driven almost entirely by improvements in automated processing rather than increases in telescope time or human workforce. The pattern that emerges from surveying all of these developments together is one of capability expanding on a curve that shows no sign of flattening. The telescopes become more sensitive each generation. The algorithms become more sophisticated as training datasets grow larger, and architectural innovations improve their ability to extract signal from noise. The data pipelines become faster as computational hardware improves and software engineering matures. The coordination infrastructure connecting observatories, researchers, and operational users around the world becomes more robust and more automated. Events that would have been missed entirely in the 1990s, either because the telescopes lacked the sensitivity to detect them, or because the processing pipelines did not exist to identify them in real time, are now detected, characterized, and distributed to the global research community within hours of occurrence. The sky is becoming more legible in a way that feels gradual from inside the process, but looks dramatic when viewed across decades. This expanding legibility has a specific and immediate relevance to the events of early April 2026. The comet now approaching perihelion was discovered earlier than any previous member of its family by instruments that did not exist a generation ago, processed by algorithms that did not exist a decade ago, and is being tracked with a precision and continuity that would have been impossible to sustain using the observational infrastructure of even the recent past. When it reaches the corona on April 4th, The data collection apparatus that will be recording the event represents the cumulative product of 30 years of accelerating capability development in solar and planetary astronomy. Every sensor will be active, every pipeline will be running. The analysis will begin before the perihelion passage is even complete, with automated systems flagging anomalies in real time and distributing alerts to researchers who will be watching their screens at observatories and universities and space agency operations centres around the world. Somewhere in the data that emerges from those hours, the answer to a question that has been sitting open in the solar physics literature for decades may finally take shape. The question of whether a large sun-grazing comet can influence the behaviour of a magnetically active corona, whether the triggering hypothesis has any physical reality, whether Alfvén's theoretical mechanisms operate at the scales this event provides, will have more observational constraint after April 4th than it has ever had before. The answer might be a clear confirmation. It might be a clear refutation. It might, in the way of complex systems studied for the first time at adequate resolution, turn out to be something more surprising than either possibility. What it will not be is unobserved, and in science that is where every answer begins. Part 15, April 4th, 2026, the moment of truth. Everything that has been building for weeks, for months, for centuries if you count the journey from the outer solar system, reaches a single point on April 4th, 2026. As the date approaches, observatories around the world and in space converge their attention on a small, brilliant object threading through the inner solar system at a speed that defies intuitive comprehension. SOHO's coronagraph begins tracking it as it crosses into the field of view. Solar Orbiter adjusts its instruments. Parker Solar Probe is already positioned in the inner solar system, closer to what is about to happen than any human-made machine has ever been during such an event. On Earth, the Daniel K. Inouye Solar Telescope is recording the Sun in multiple wavelengths simultaneously, hunting for any change in the chromosphere or corona that might signal the comet's influence before perihelion even arrives. The possible outcomes sit in a range that reflects everything uncertain about this event. At one end, the comet begins disintegrating at a distance before it ever reaches the deepest corona. The nucleus fragments too early, the pieces vaporize individually, and what reaches perihelion is not a coherent object but a dispersed trail of plasma, spectacular in imagery, relatively uneventful in terms of solar interaction, a beautiful death noticed by solar observatories and no one else. In a middle scenario, the nucleus survives deep into the corona as Lovejoy did, then fragments dramatically under tidal forces and radiation pressure. The corona lights up with comet material visible in SOHO imagery. A trail of plasma threads along magnetic field lines. Solar scientists get the observational data they have been waiting for to either confirm or contradict hypotheses about comet corona dynamics. The Sun continues its regular activity, releasing a CME or two that were already forming, and researchers spend the next 2 years analysing whether any of the Sun's behaviour was influenced by the comet's arrival. At the other end of the range, something more dramatic happens. You know what that scenario looks like by now. You have followed the chain of events through 9 parts of this story. The details are not the point anymore. The point is that the range of possibilities has not collapsed to a single known outcome. Not yet. The uncertainty remains genuine and quantifiable and real. What the moment of perihelion represents beyond its immediate astronomical interest is a test of a particular kind of scientific humility. The humility to acknowledge that complex systems do not always announce their turning points in advance. The Carrington event of 1859 was not predicted. The emergence of Comet Lovejoy from behind the Sun in 2011 was not expected. The discovery of Oumuamua as the first confirmed interstellar visitor happened because a routine survey happened to be pointed at the right place at the right time. The universe does not schedule its most important moments for human convenience. It does not put warning labels on black swan events. It does not respect the difference between the most likely scenario and the rare alternative. It simply proceeds, according to physics and mathematics and the accumulated dynamics of 4.5 billion years of solar system evolution, and occasionally, in doing so, it produces something that rewrites what we thought we knew. On April 4th, 2026, a comet that has been travelling toward the Sun for possibly thousands of years reaches the end of its journey. Scientists with the most sophisticated instruments in human history will be watching. The outcome is uncertain. The physics is extraordinary. The window into processes we have never been able to observe at this scale is, briefly, open. And whatever happens next, the most important events in science have always been the ones we only fully understood after they were already over. The question is whether we are living through one of those moments right now, or simply through the dress rehearsal for one we have not yet imagined.